Welcome to the SolveForce podcast series, where we discuss and decode the technical networks that connect our world. Hi, we're Alex and Taylor. For today's deep dive, imagine a network router. Just, hanging on a telephone pole in the middle of a remote sun-baked desert.
Yeah, completely exposed.
Right. There are no biometric locks, no security guards, no, reinforced concrete walls protecting this thing.
Just a metal box on a pole.
Exactly. So a threat actor with a ladder and a screwdriver climbs up, pries open the metal casing, and attempts to hack into the hardware. They want to access the central energy grid.
Which is a very real scenario, by the way.
Oh, yeah, terrifyingly real.
Yeah.
But the absolute millisecond that casing is breached, before the attacker can even connect a cable to it, the router permanently locks its cryptographic keys. It severs power to its own volatile memory, purges its storage, and essentially, it self-destructs its own brain.
It completely bricks itself.
It bricks itself to protect the grid.
It is literal spy movie technology happening right now on our utility poles. And, it represents a massive paradigm shift in how we think about protecting data.
Yeah, it's wild.
Because for decades, the entire cybersecurity industry was built on this very human, very geographical concept of safety. We relied on physical boundaries.
Like actual walls.
Right, actual walls. If you were inside the corporate building, behind the firewall, you were trusted. And if you were outside, well, you were untrusted. But the scenario you just described on that utility pole, that happens in a world where the physical perimeter no longer exists.
The walls have just completely evaporated.
Exactly.
I mean, you look at modern enterprise networks today, and the architectural logic we relied on for, 30 years?
At least 30 years, yeah.
It is just buckled. The data isn't sitting in a locked basement anymore. It's distributed across AWS, Azure, and dozens of SaaS providers.
Right, it's everywhere.
And the workforce isn't swiping badges at a turnstile either. You are sitting in coffee shops or airport lounges or your home office, connecting over, standard residential internet.
Which is inherently insecure.
Completely. So today, our mission for this deep dive is to decode the mechanics of this new reality. We are unpacking the concept of Zero Trust Network Access, or ZTNA for short.
The buzziest of buzzwords, but we're going to explain what it actually means.
Exactly. We're going to explore exactly why the legacy castle and moat security model is officially dead, and, more importantly, how modern networks actually secure data when there are absolutely no borders left to defend.
And we are going to dive really deep into the underlying mechanics of how this is actually achieved, because whether you are an engineer actively designing these environments, or maybe you're an executive trying to understand how to, enable a hybrid workforce without exposing your entire company to a catastrophic ransomware event.
Nobody wants that.
Right. Nobody wants that. You have to understand the physics of this transition. And to do that, we really have to start by diagnosing the failure of the old model.
The old castle and moat.
Exactly. Because the genius of Zero Trust only really makes sense when you understand the sheer operational agony of the architecture it is replacing.
Agony is a good word for it. So let's talk about that legacy architecture. The hub-and-spoke wide area network. The classic castle and moat.
The dinosaur.
Yeah, the dinosaur. Historically, if you built an enterprise network, you anchored it around a massive centralized corporate data center. That was your hub.
Right.
And every remote branch office, every manufacturing plant, every little retail store, those were the spokes. And they all connected back to that central data center using these private, dedicated telecom circuits.
Usually MPLS.
Right. Multi-protocol label switching.
Yeah, MPLS was the gold standard for a very, very long time. And for good reason, honestly. When a business bought an MPLS circuit from a carrier, they were essentially buying a private, carved-out lane on the information superhighway.
Like a VIP lane?
Exactly like a VIP lane. It wasn't subject to the wild, best-effort congestion of the public internet. The carrier used label-switched paths to route packets based on short path labels rather than complex network addresses.
Which gave businesses, deterministic routing?
Yes, deterministic routing. You had guaranteed bandwidth, you had strict service level agreements for uptime, you had predictable latency. I mean, it was highly engineered and incredibly reliable, but staggeringly expensive.
Staggeringly expensive. Right, because you were paying for the privilege of that private road.
Exactly.
Because all of your corporate traffic from every branch office across the globe was funneled onto these private roads leading back to your central data center. That data center became the logical place to build your defensive moat.
It was the choke point.
Right. You routed all the traffic through one single ingress and egress point, and you just stacked a mountain of physical security appliances right at that gate.
And that physical stack was the literal moat. Network engineers would rack and stack these towering arrays of physical hardware.
What kind of hardware are we talking about?
Oh, everything. You had your next-generation firewalls doing deep packet inspection. You had intrusion prevention systems, IPS, looking for malware signatures, secure web gateways filtering out malicious URLs.
Wow, just everything.
Data loss prevention engines trying to ensure credit card numbers weren't leaking out. Every single packet that wanted to leave the corporate network and go out to the internet or come from the internet into the corporate network had to traverse this massive physical gauntlet.
Right there in the central data center.
Exactly.
Now, on paper, that sounds incredibly robust. You put all your heavy artillery right at the single gate to the castle.
Makes sense, logically.
It does. But the fatal flaw of this design wasn't the strength of the firewall itself. It was the philosophical assumption the firewall made about what happened after you passed through that gate.
Yes.
There's a concept of implicit trust.
Implicit trust is what ultimately destroyed the legacy network.
Yeah.
Under this model, the security perimeter was entirely spatial.
Meaning based on location.
Right. If you plugged your laptop into an Ethernet port inside the corporate headquarters, or, if you connected from a remote branch over that private MPLS line, the network looked at your physical location and basically concluded, well, you are inside the walls, therefore you must be safe.
Just because of where you're sitting.
Exactly. Once you authenticated, you were granted access to a flat internal network.
And a flat network is basically a playground for lateral movement, right?
Oh, absolutely. The routing tables were designed for maximum connectivity. If you were a verified user, your machine could theoretically ping, scan, and establish TCP handshakes with almost any other server inside that environment.
Because the firewall didn't care anymore.
Right. The firewall at the perimeter didn't care what you did once you were inside, because its only job was guarding the front door.
Wow. So it was an architecture optimized for connectivity, not isolation.
Precisely. And to be fair, that worked reasonably well when all the applications and all the users were actually inside the building.
Right, back in 2005.
Yeah, back in the day. But then, 3 massive tectonic shifts occurred in the industry that broke this model from a pure physics perspective.
Okay, let's break those down. What was the first disruptor?
The first was the explosive adoption of software as a service, or SaaS.
The end of shrink-wrap software.
Right. Applications like Microsoft 365, Salesforce, Workday, ServiceNow, these became the absolute lifeblood of the modern enterprise. But suddenly, the servers hosting these applications were no longer sitting in the basement of that central data center.
They were out on the internet.
They were hosted out on the public internet, in Microsoft and Salesforce data centers. The king's gold had literally been moved outside the castle wall.
That's a great way to put it. The gold is gone. So what was the second shift?
That migration was compounded by the second disruptor, which is infrastructure as a service.
Like AWS.
Exactly. Companies realized they didn't want to be in the business of maintaining physical cooling systems and diesel generators and hardware refresh cycles for their custom applications. It's a headache.
Yeah, let Amazon handle the diesel generators.
Right. So they took their proprietary workloads, their customer databases, their internal APIs, and they migrated them to public cloud providers like AWS, Microsoft Azure, Google Cloud.
So now the data center is just what?
Now, the data center is basically just an empty room with some legacy mainframes and a massive, expensive firewall stack.
Which brings us to the third and final nail in the coffin. The workforce became highly distributed.
Yes. Even way before the pandemic accelerated it, users were leaving the building.
Right. You have sales teams working from airport cellular hotspots, executives logging in from hotel Wi-Fi, and obviously a massive hybrid workforce operating from their home routers.
Which, again, are not secure.
No. So the gold is in the cloud, the knights are scattered all across the countryside, and the castle is just sitting there with an incredibly expensive moat protecting absolutely nothing of value.
It's ridiculous when you frame it like that, but that's exactly what happened. And this misalignment between the physical network architecture and the reality of where work was actually happening created this operational nightmare known as the trombone effect.
Or hairpinning.
Yeah, hairpinning. This is where the physics of the legacy network actively begin to sabotage the business.
Let's really break down the mechanics of the trombone effect for a second, because it illustrates exactly why you can't just patch a legacy network. You have to replace it.
Right.
So imagine you were sitting in a branch office in Denver, Colorado. You need to pull up a customer record in Salesforce, which happens to be hosted in a cloud data center in Seattle, Washington.
Okay.
Now, in a logical world, your laptop would just make a TLS encrypted connection straight over the internet from Denver to Seattle.
It's the shortest path.
Exactly. But the legacy hub-and-spoke architecture actively prevents that direct connection.
Because the network designers still believe that every packet must be inspected by the security stack.
And the security stack only exists in the central data center in New York.
Right.
So your laptop in Denver sends a packet destined for Seattle. But the local branch router intercepts it, takes that packet, encapsulates it, and forces it onto the private MPLS circuit.
Sending it all the way across the country.
Yes, all the way to New York. The packet arrives in New York, gets decapsulated, and has to literally wait in line to be processed by the physical firewall stack.
The gauntlet.
The gauntlet. The firewall runs its deep packet inspection, checks its intrusion prevention rules, and finally says, okay, yeah, this is a legitimate Salesforce API call. It then spits the packet out onto the public internet where it travels all the way back across the country to Seattle.
And then, and this is the worst part, the response packet from Salesforce has to take that exact same convoluted, absurd path backwards.
Seattle to New York, through the firewall, back onto the MPLS circuit, New York to Denver.
Yep. If you draw the path on a map, it looks like the slider of a trombone extending across the continent and retracting back.
Hence the name. I mean, you were actively fighting the speed of light at that point.
You are. When you introduce that much geographical distance, you are adding massive round-trip latency to every single TCP handshake.
You take a connection that should have, what, a 30 millisecond ping?
And you turn it into a 300 millisecond sluggish nightmare. TCP windowing breaks down, applications time out, video calls become jagged and completely unworkable.
Just a terrible user experience.
And the financial tragedy here is that the business is paying millions of dollars a year for premium MPLS bandwidth just to haul traffic thousands of miles out of its way, only to eventually dump it onto the public internet anyway.
It is financially ruinous and, operationally destructive.
Yeah.
The user experience degrades so severely that employees just start trying to bypass the corporate network entirely.
Which introduces shadow IT, people using personal VPNs, personal hotspots.
Right. But even beyond the latency and the cost, this model fundamentally fails to protect against modern threat actors because of that lateral movement vulnerability we touched on earlier.
Yeah, let's talk about the attackers for a minute. Because if I am a ransomware syndicate, I am not trying to bash my way through your massive New York firewall. That's way too hard.
You look for the weakest link.
I'm going to look for the softest target on your extended perimeter.
Give me an example.
Well, maybe it's a receptionist's laptop at a tiny branch office in Ohio that someone, accidentally plugged an infected USB drive into.
Or maybe I execute a phishing campaign and harvest the VPN credentials of a mid-level manager who's just working from home.
Exactly. And once the attacker authenticates using those compromised credentials or establishes a foothold on that low-tier branch device, the perimeter firewall in New York becomes entirely irrelevant.
The threat is already inside the house.
Exactly. Because of the implicit trust of that flat network we talked about, that single compromised laptop in Ohio becomes a launchpad.
So what does the attacker do next?
The attacker quietly deploys a scanning tool. Maybe they run an Nmap sweep and map out the internal topology of the network.
And the New York firewall doesn't see this.
No. The firewall in New York isn't inspecting east-west traffic, meaning traffic moving laterally from server to server or branch to data center, because it's too busy choking on all the north-south internet traffic from the trombone effect.
Wow.
So the attacker just moves laterally, completely unimpeded. They escalate privileges, find the Active Directory domain controllers, locate the high-value database servers in AWS that are tethered back to the data center.
And then they deploy the encryption payloads.
And the entire enterprise goes dark.
Just from one phished password in Ohio.
Yep. The realization that physical location can no longer be a proxy for trust is what birthed the zero trust paradigm shift. The whole mantra of the industry became never trust, always verify.
Never trust, always verify.
All right. If we cannot secure a physical location because the perimeter has dissolved, we must secure the transaction itself. We have to shift from network-centric security to identity-centric or resource-centric security.
And this requires a complete rewiring of how the network actually thinks. Because in the old network-centric model, your IP address basically was your identity, right?
Yeah, pretty much. If your IP address fell within the subnet allocated to the corporate headquarters, the router trusted you.
But under Zero Trust Network access, your IP address is essentially meaningless.
Completely meaningless. It doesn't matter if you are sitting at the CEO's desk connected to the corporate LAN, or if you are logging in from a public Wi-Fi network at a coffee shop in Prague.
The network treats both connections with the exact same level of extreme suspicion.
Yes. Under ZTNA, access to everything is denied by default.
Denied by default. That's huge.
The transition from default allow internal routing to strict default deny is the foundational pillar of the entire architecture. Since the network inherently distrusts you, it forces you to continually prove your right to access a specific resource.
It doesn't grant you access to a network at all, does it?
No, not at all. It grants you a heavily brokered, highly specific connection to a single application. Nothing more.
And the way it decides whether to build that specific connection is by calculating what's called a contextual risk score.
The contextual risk score is where the real intelligence of the system lives, because it's not just a simple password check anymore. A password can be stolen, as we just established.
Right. Even a multi-factor authentication token can be intercepted through, like, a man-in-the-middle proxy attack.
Oh, absolutely. MFA fatigue, proxy attacks, it happens every day. To truly establish trust, the ZTNA engine has to ingest multi-dimensional telemetry from various sources simultaneously.
What are those dimensions? Walk us through the telemetry.
Well, it starts with user identity and role. The ZTNA control plane integrates natively with an enterprise identity provider, or IDP, like Microsoft Entra ID, Okta, or Ping Identity.
Okay, so it checks who you are.
It checks the cryptographic token to verify your identity, yes. But then it queries the directory to understand your role.
Right, what you're actually allowed to do.
Exactly. Are you an HR representative? Are you a database administrator? Or are you just a marketing intern? It enforces the principle of least privilege access. A marketing intern might be perfectly authenticated, but their role actively denies them routing access to, say, the financial ledgers.
Makes sense. But identity is just the first dimension. Because even if you are the legitimate database administrator with the correct credentials, if you are trying to log into the production environment from, I don't know, your teenager's malware-infected gaming PC,
the network should absolutely slam the door in your face.
yes.
And this is where device health and posture comes into the equation.
How does it know the health of the device?
The local endpoint agent installed on the machine provides deep contextual telemetry about the hardware and software itself.
Like what?
Like, is the operating system running the latest security patches, or is it vulnerable to a known exploit? Is the corporate antivirus actually running, and are its signature definitions up to date? Is the host firewall enabled?
Wow, so it's checking all of that in real time.
All of it. It even checks for the presence of a hardware-bound corporate certificate to ensure this is an actual company-issued asset and not just a personal iPad. If any of those posture checks fail, if the risk score elevates past the acceptable threshold, access is denied, regardless of whether you have a valid password.
That is incredibly strict.
It has to be. And the engine goes even further by analyzing the metadata of the connection itself. It looks at geographic context and behavioral anomalies.
Ah, so where you are physically located.
Exactly. Let's say you successfully authenticate and pull a file from a server in New York. And then, 12 minutes later, there is an authentication attempt using your exact credentials originating from an IP address in Eastern Europe.
Right, which is physically impossible.
Exactly. The system triggers an impossible travel alert. It knows human physics prevents you from traveling that distance in 12 minutes, so it assumes the session token was hijacked, and it immediately blocks the access.
What about time-based anomalies?
It evaluates the time's day against your baseline behavioral patterns, too.
So if I'm a junior accountant who historically only works from 9 to 5 on weekdays,
and you suddenly attempt to initiate a massive database export at 3:00 a.m. on a Sunday,
yeah, that looks super suspicious.
the ZTNA engine will dynamically enforce a step-up authentication challenge or just deny the action entirely until it can be verified by a human.
That is so smart.
Yeah.
And here's the truly revolutionary part to me. This verification isn't just like a bouncer checking your ID at the front door and then letting you roam the club for the rest of the night.
No, because that was the flaw of the legacy VPN.
Exactly. With a traditional VPN, you authenticate at 8:00 a.m., the IPsec tunnel opens, and it basically just stays open for 10 hours.
Yep.
So if your machine gets infected with a worm at noon, that worm just rides the already open VPN tunnel straight into the corporate data center.
It's a free pass. Zero Trust solves this through what we call the continuous adaptive trust loop, or the CIT loop.
The CTO. Explain how that works in practice.
The CIT loop means the network is constantly, relentlessly watching the session. Authentication is not a one-and-done event. It is a continuous, dynamic state.
Okay.
Let's say you pass all the initial checks, you are working in Salesforce, everything is fine. But 30 minutes into your session, you walk out of your house, and your laptop automatically joins an insecure, open public Wi-Fi network at a cafe down the street.
Right, which happens all the time.
Or worse, a background process suddenly disables your local endpoint detection and response agent.
So the environment just materially changed. The risk posture shifted.
And the local ZTNA agent on your machine instantly detects that state change. It fires a telemetry update to the central policy decision point in the cloud.
The brain.
The brain, yes.
Right.
The policy engine recalculates your risk score in real time, sees that it now exceeds the permissible threshold, and it instantly tears down the active data path.
Wow.
It doesn't wait for you to log out. It actively revokes your access the millisecond your machine becomes non-compliant.
Okay, hold on. I have to interject here. Because if you describe this to a traditional network engineer, their blood pressure is going to spike.
Oh, I know. I've seen it.
I mean, think about it. If the network is constantly verifying identities with a cloud directory, checking antivirus statuses every 3 seconds, pulling GPS coordinates, and analyzing every single packet against a dynamic policy engine, the laws of physics dictate you are going to introduce massive processing latency.
It sounds like it would, yes.
If I have to be interrogated thousands of times a minute, my video calls are going to lag, my SSH sessions will stutter, and literally no actual work will get done. How is this computationally sustainable?
It is a brilliant question, and it highlights exactly why Zero Trust isn't just a simple software update. It requires a completely new network topology.
You can't run this on a Linksys router.
You cannot execute this level of continuous cryptographic inspection on a cheap branch router, and you certainly can't route all this traffic back to a central data center, because then we are just recreating the trombone effect we just complained about.
Right, so how do they do it?
To make continuous verification work without latency, we rely on the architecture of Secure Access Service Edge, or SASE.
SASE. Okay, so we are taking the massive processing power required for these security checks and moving it out of the data center and into the cloud.
Precisely. SASE platforms take the entire security stack, the firewalls, the zero trust engines, the data loss prevention, and they distribute them across hyperscale cloud points of presence, or POPs, all over the globe.
Massive data centers everywhere.
Everywhere. Companies like Zscaler, Palo Alto Networks, Cloudflare, they have built massive computational nodes in hundreds of cities. When you are sitting in Denver, your local ZTNA agent uses BGP Anycast routing to automatically find the absolute closest cloud POP.
So my laptop isn't talking to a server in New York anymore. It's establishing a secure, encrypted tunnel to a cloud data center that might literally be 2 miles away from my house, sitting on the same internet backbone as my local ISP.
Yes. And these hyperscale cloud nodes operate at line rate. They have vast arrays of elastic compute power.
So it can handle the load.
Easily. They can intercept your traffic, decrypt the TLS session, inspect the payload for malware, verify your contextual risk score against the policy engine, re-encrypt the packet, and forward it on in single-digit milliseconds.
That is incredibly fast.
And because we are utilizing direct internet access, or DIA, your traffic goes from your laptop to the local cloud POP for inspection, and then directly over the high-speed peering links to the Salesforce data center in Seattle.
Wow. We completely bypass the legacy corporate network.
Completely. There is no MPLS circuit. There is no backhaul to New York. By checking everything continuously in the cloud right at the edge next to the user, Zero Trust actually improves the network speed.
It's a win-win.
You get military-grade deep packet inspection, but the latency drops because the routing is infinitely more efficient.
It flips the old paradigm totally on its head. Security is no longer a bottleneck. It is actually an optimized routing path.
Exactly. But this brings us to a really fascinating technical challenge. We've established how the user securely connects to the cloud security engine. But how does the cloud security engine securely connect the user to an internal, proprietary corporate application?
Right, because if a company has a custom billing application sitting in AWS, they obviously cannot expose that application to the public internet.
No, absolutely not. The moment you put a public IP address on the internet, it gets scanned and attacked by automated botnets within minutes.
Seconds, even. Which brings us to the actual execution layer, the mechanics of invisible networks. How do we grant a remote worker access to a private application without actually putting that application on the internet?
Because legacy VPNs handled this terribly.
Tell me about it. A traditional VPN gateway sat right on the edge of the corporate network, right on the perimeter, and it literally just listened for incoming connections.
It had an open public-facing port.
Right, like UDP port 500 for an IPsec tunnel, or TCP port 443 for an SSL VPN. It essentially stood there, completely visible to the entire internet, broadcasting its existence and asking people to send it passwords.
Hey, I'm a VPN, please hack me.
Exactly. And because the VPN gateway was visible, it was infinitely vulnerable. It could be targeted by volumetric distributed denial of service attacks.
DDoS, yeah. Where botnets just overwhelm the port with junk traffic and crash the appliance.
But more dangerously, it was susceptible to zero-day exploits.
This is the real fear. If a state-sponsored hacker discovered a vulnerability in the VPN's parsing engine, they could send a maliciously crafted packet directly to that open port.
And the VPN would try to process it.
The VPN tries to process the packet, the buffer overflows, and the attacker gains root execution privileges on the gateway itself.
Game over.
Game over. And because the VPN sits on the edge of the flat internal network, compromising the VPN means you have compromised the entire enterprise.
The attack surface was massive simply because the door was visible. So Zero Trust fundamentally alters this by decoupling the planes of operation.
Decoupling is the magic word here.
In a traditional network, the brain making the routing decisions and the muscle moving the actual data packets were fused together in the same physical router or firewall.
Right, control and data were merged.
But in a ZTNA architecture, we strictly separate the control plane from the data plane.
This separation is the absolute key to invisibility. The control plane is the policy decision point. That's the brain sitting in the SASE cloud.
Right.
The data plane is the policy enforcement point. That's the gateway sitting in front of your private application in AWS. The critical mechanic here is that all authentication happens out of band.
Out of band, meaning the conversation about whether you are allowed to connect happens on a completely different channel than the actual application data itself.
Yes. When your laptop wants to access the billing app, the ZTNA client talks strictly to the control plane using federation protocols like SAML 2.0 or OpenID Connect.
You prove your identity to the brain first.
You prove it to the brain. The actual billing application and the gateway protecting it have absolutely no idea you exist yet.
Right. And meanwhile, the gateway protecting that billing application, the policy enforcement point, is utilizing what we call dark address space.
Dark space.
It does not have any inbound listening ports open to the internet at all. None. Instead, it spins up lightweight outbound connectors.
Outbound only.
These connectors reach out from the private AWS environment up to the SASE cloud POP, establishing a persistent outbound-only TLS tunnel.
So because the connection is initiated from the inside out, the enterprise firewall allows it. But there is no open port for a hacker to find on a Shodan scan.
The application is completely cloaked. Invisible.
Invisible.
But if the application is invisible and not listening for inbound traffic, how does my laptop actually connect to it once the control plane validates my risk score and gives me the green light?
Through an incredibly elegant cryptographic mechanism known as single packet authorization, or SPA.
Network engineers sometimes refer to the concept as a knock-on port.
Yes, knock-on port.
I absolutely love the engineering behind SPA. Let's really dive into the cryptographic weeds here, because the policy enforcement point gateway, protecting the app, is maintaining a strict default deny posture.
Right, it sits there silently, dropping all inbound TCP and UDP packets.
If a threat actor pings it, it doesn't respond. If an automated script runs a full TCP SYN scan against all 65,000 ports,
the gateway acts like a black hole. It consumes the packets and sends absolutely nothing back.
so to the outside observer, the gateway just doesn't exist. The IP address appears completely dead.
But the gateway's operating system kernel is quietly listening.
It's waiting.
Waiting. When your client is fully authorized by the control plane issues your client a highly specific cryptographically signed token. To initiate the connection, your ZTNA client constructs one single solitary SPA packet.
And it's usually a UDP packet, right?
Yeah.
Because TCP is too chatty.
Exactly. A TCP connection requires a three-way handshake, SYN, ACK, ACK. If the gateway responded to a SYN packet, it would instantly reveal its presence to a port scanner.
Which ruins the whole invisibility thing.
Right. By using a single UDP packet, it's a fire and forget transmission.
So the client takes the authorization token, adds a strict timestamp, and encrypts the entire payload, usually generating an HMAC.
A hash-based message authentication code.
It fires this single SPA packet at the silent gateway. Now, normally the gateway's firewall rules drop everything. but the gateway is configured so that its kernel space, specifically the net filter framework, intercepts this exact type of packet before it even reaches the user space applications.
The kernel grabs the packet, decrypts the HMAC, validates the cryptographic signature against the control plane's public key, and critically, it checks the timestamp.
Ah, the timestamp is vital to prevent replay attacks.
Absolutely. If a malicious actor happens to be sniffing the internet traffic, intercepts your SBA packet, and tries to replay it to the gateway 5 minutes later, the kernel will see that the timestamp has expired and silently drop it.
The packet is only valid for a window of a few seconds.
Literally seconds.
Yeah.
But if the signature is valid and the timestamp is fresh, the magic happens.
What does the gateway do?
The gateway dynamically alters its own firewall rules in real time. It opens a temporary pinhole specifically and only for the source IP address of your client.
Oh, wow.
It allows your client to establish a mutual TLS or NTLS encrypted session through that pinhole. And the millisecond that session is established, the firewall rule reverts and the pinhole vanishes.
It closes right behind you.
To anyone else scanning the internet, the port remains closed the entire time.
It is an extraordinary piece of engineering. I mean, it effectively neutralizes entire categories of network attacks.
Yeah.
You cannot exploit a zero-day vulnerability in a listening service if you cannot even establish a TCP handshake with that service.
It's impossible.
It's like a secret speakeasy, but taken to a cryptographic extreme.
I like that analogy.
It's not just a club with a bouncer standing outside checking IDs. It's a literal, solid brick wall with no door.
Just bricks.
Right. A hacker can walk up and knock on the bricks all day, run automated scanners against the bricks, and absolutely nothing happens. But if you walk up and whisper the exact cryptographically signed password, the door literally materializes out of the bricks for exactly 3 seconds.
You step inside the tunnel, and it instantly turns back into a solid brick wall behind you.
That is just so cool. By eliminating the public listening port, ZTNA fundamentally removes the external attack surface of the network perimeter. The applications are cloaked.
They are completely hidden. But this leads us to the next critical layer of the architecture, because SBA gives us a highly secure, invisible front door.
Right.
But as security professionals, we must assume a state of continuous compromise. What happens if a threat actor manages to steal a fully authenticated corporate laptop while that MPLS tunnel is open? Then the attacker is now physically inside the data center environment.
Exactly. If we rely entirely on that front door, we are right back to the castle and moat problem on the inside. How do we stop them from moving laterally once they are through the door?
Which means we have to bring zero trust into the interior of the data center itself. We have to partition the environment so that a breach in one area doesn't cascade into a catastrophic total system failure.
We have to move from the edge to the core.
Segmentation from macro to micro.
Right, because just because you are granted access to the speakeasy doesn't mean you have the keys to the manager's office, the liquor cabinet, and the cash register.
Good point.
We have to compartmentalize the internal network. Historically, network engineers started with the broad strokes, a concept known as macro segmentation.
Macro segmentation is essentially setting up different logical rooms within the data center based on broad categories of risk, right? You establish strict routing boundaries.
Yes. You might take all your public-facing web servers and put them in a demilitarized zone, or DMZ.
Okay. You put your employee virtual desktops in a corporate user zone. Your core applications go in a production data center zone. And your crown jewels, your highly regulated customer databases, they go into a strictly isolated database and storage zone.
And the mechanism used to enforce these broad boundaries on enterprise switching hardware is virtual routing and forwarding, or VRF.
VRF, yes. To understand why VRF is so powerful, you have to understand how a network switch operates fundamentally.
Let's break it down.
A basic switch operates at layer 2 of the OSI model. It uses MAC addresses and VLANs to separate traffic.
But VLANs can be hopped or bypassed if a router connects them, right?
Easily. VRF operates at layer 3. It allows network engineers to partition the actual routing table itself. You can create multiple, completely independent routing tables on the exact same physical chassis.
So it's not just putting a tag on a packet, it's physically separating the map the router uses to send the packet.
Exactly. Think of the physical switch as a massive corporate skyscraper, and the VRF routing tables as completely separate sealed elevator shafts.
Okay, I can picture that.
The traffic from the guest zone is in shaft A, and the traffic from the database zone is in shaft B. Even though they exist inside the exact same physical hardware, they have separate routing logic, separate memory space, and they cannot see or interact with each other natively.
So a packet in the guest VRF literally has no topological awareness that the database VRF even exists.
The route simply isn't in its table.
So if a server in the guest zone gets compromised and it tries to ping a server in the database zone, it doesn't know where to send it.
It's like asking an elevator to go to a floor that isn't on the button panel. To actually move traffic between those zones, the packet has to physically leave the switch, be routed out to an internal firewall, undergo deep packet inspection, and then be routed back into the other VRF.
That is macro segmentation in a nutshell.
Yeah.
And it's highly effective for coarse-grained control in traditional static data centers.
Static being the operative word there.
Right, because as enterprises migrated to modern elastic cloud environments and adopted containerization, macro segmentation completely fell apart. We ran headfirst into what architects call the problem with IPs in the cloud.
This is a huge problem because legacy internal firewalls and routing tables rely exclusively on IP addresses.
The rule literally says, allow IP 10.0.5.20 to communicate with IP 10.0.9.50 on TCP port 443.
The security is inextricably tied to the network address.
Yes, network-centric security. But in modern environment running Kubernetes or serverless functions, IP addresses are highly ephemeral. They're temporary constructs.
Let's use an example to illustrate this. Imagine a retail company on Black Friday.
Okay, busiest day of the year.
Their web application gets slammed with traffic. The Kubernetes orchestrator detects the load and dynamically spins up 50 new web server containers to handle the spike.
Right, elastic scale.
Each of those containers is assigned a random IP address from a dynamic pool. They process customer transactions for exactly 12 minutes, the load subsides, and the orchestrator destroys the containers. The IP addresses vanish back into the pool.
So if you were trying to maintain a static list of IP-to-IP firewall rules in an environment where workloads live and die in a matter of minutes, your firewall CPU will literally choke to death just trying to update its rule base.
It can't keep up. The security policies would be obsolete before the network admin even finished typing them into the console.
You end up with massive rule bloat, stale rules that leave security holes open, and continuous application outages.
It is an impossible administrative burden, and that reality forced the industry to adopt the surgical approach, microsegmentation.
Microsegmentation.
With microsegmentation, we entirely abandon the IP address as the basis for security enforcement. We decouple security from the network topology completely.
So what do we use instead?
We introduce tag-based, workload-centric policies. The rules are based on semantic, logical tags that are attached to the workload itself, regardless of where it lives on the network.
This requires a major shift in how you write the rule. Give us a conceptual breakdown of a microsegmented policy.
Instead of using subnets, the security architect writes a policy based on the metadata of the application. The rule might state, source tag environment, production, application, billing, tier, web destination, tag environment, production, application, billing, tier, database, action. Allow TCP port 3306.
Notice there are 0 IP addresses, 0 VLAN tags, and 0 subnets in that entire policy declaration.
None. The orchestration system manages the state. When that Kubernetes cluster spins up those 50 new billing web servers on Black Friday, the orchestrator automatically assigns those semantic tags to the new containers.
Right as they boot up.
Yes. The hypervisor, the underlying software managing the virtual environment, reads those tags. It queries the central policy controller, downloads the correct microsegmentation profile, and instantly applies it directly to the virtual network interface car, or VNIC, of each specific container.
It intercepts the traffic before it even hits the virtual switch, let alone the physical wire.
Exactly. The enforcement point is pushed down to the absolute atomic level, the individual workload itself.
Wow.
And because the policy is tied to the tag, the security travels with the workload. If the virtual machine dynamically migrates via vMotion from a physical server in your primary data center to a backup server in a disaster recovery site,
The IP address will change, sure.
but the microsegmentation policy remains perfectly intact. It creates a localized cryptographic perimeter around every single application.
And this allows for extreme granular isolation, such as ring fencing.
Yes, ring fence.
When you are dealing with highly regulated data, say a database cluster storing PCI cardholder data, actual credit card numbers, you don't just want to restrict who can talk to it. You want to restrict who it can talk to.
Yes. Ring fencing is the ultimate defense against data exfiltration and ransomware command and control.
How does it stop ransomware?
With microsegmentation, you can draw a strict cryptographic boundary around that PCI database. You configure the policy so there is absolutely zero outbound connectivity by default.
Because a database server has no logical reason to initiate a connection to the public internet,
Yeah.
or even to the broader corporate LAN.
Exactly. So if a threat actor somehow manages to drop a ransomware payload onto that database server, maybe through a compromised administrative tool, the ransomware will try to execute. It will try to phone home to its command and control server on the dark web to download the encryption keys.
What happened?
The hypervisor intercepts that outbound request and silently drops it.
It's trapped.
The ransomware is isolated in a sterile environment. It cannot pull the keys, and it cannot scan laterally to infect neighboring servers because the microsegmentation policy denies all unauthorized east-west communication.
And for inbound access, you restrict it entirely. The only way an administrator can access that ring-fenced database is through a heavily monitored bastion host or a specific virtual desktop infrastructure gateway that requires step-up multi-factor authentication.
It's beautifully secure.
Okay, hold on though.
Yeah.
This sounds conceptually perfect, but let's look at the messy reality of enterprise IT.
Oh, it's very messy.
If you have a legacy data center with thousands of virtual machines, undocumented internal applications, custom APIs written by developers who left the company 10 years ago.
A nightmare.
If you suddenly deploy microsegmentation and switch the entire environment to default deny, wouldn't you accidentally block thousands of legitimate undocumented connections? Doesn't the whole company just grind to a catastrophic halt?
That is the single greatest fear of every chief information security officer. And if implemented recklessly, it is exactly what happens.
You cause a self-inflicted denial of service attack on your own business.
Yep. You cannot just flip the zero trust switch in a legacy environment. Deploying microsegmentation requires a rigorous, phased deployment lifecycle, and the mandatory first step is application dependency mapping, or ADM.
We have to map the chaos before we can control it. How does ADM actually work under the hood?
Before you write a single blocking rule, you deploy lightweight telemetry sensors across every workload in the environment. These sensors don't block anything, they just watch.
Like security cameras.
Exactly. They record every single TCP handshake, every UDP flow, and every DNS request. The system ingests all this raw telemetry data into a massive cloud analytics engine.
And then what?
It uses graph database technology to visualize the traffic flows, building an interactive, multi-dimensional map of exactly which servers are talking to which servers, over what ports, and at what frequency.
So the security team can actually visualize the living, breathing reality of the network, rather than relying on an outdated Visio diagram from 5 years ago.
Precisely. The map reveals the truth. You see the documented, expected traffic, the web servers talking to the databases, but you also uncover the hidden, chaotic dependencies.
Like what kind of hidden things?
Oh, you find a forgotten legacy backup script that runs at 2:00 a.m. on the third Sunday of every month, pulling data across an obscure port.
Yikes.
Or you find a developer's workstation making direct SQL queries into a production database.
Which should never happen. Once you have that visibility, you can begin to craft the microsegmentation policies. But you still don't turn them on, right? You use a phased approach.
Yes. You draft the tag-based policies, but you deploy them in monitor-only mode.
Ah, monitor only.
The hypervisor acts as if the policy is active. It inspects the packets against the drafted rules. If a packet violates the rule, the hypervisor lets the packet pass so the application doesn't break, but it generates an alert flag in the central console.
So you run in monitor-only mode for a few months, or maybe a full month, to capture end-of-month financial closing processes.
Exactly. The security team reviews the alerts, discovers that the legacy backup script would have been blocked, and they surgically tweak the policy to allow it.
They iterate on the rules until the alert log goes quiet.
And only after the environment is completely understood and the policies are perfectly refined and tested against the live traffic baseline, do you finally move the system from monitor-only to block and audit mode.
The perimeter clamps down at the atomic level, and you have successfully implemented zero trust inside the data center without breaking the business.
It's an incredibly deliberate surgical operation.
So we've secured the cloud connection with SASE. We've secured the internal data center with microsegmentation. We have locked down the pristine climate-controlled environments.
But we aren't done.
No, we are not. Now we have to face the final and perhaps most difficult frontier of network architecture. We arrive at zero trust at the physical edge.
This is where theoretical security models face their ultimate stress test against the physical world.
Because in a cloud data center, you have biometric man traps, armed security guards, and server racks enclosed in locked cages. You have absolute physical sovereignty over the hardware.
But the modern enterprise network extends far beyond those walls.
We are talking about highly rugged, physically insecure environments, an automated robotic assembly line on a factory floor, a cellular 5G base station sitting on top of a building, or the scenario we opened the episode with, a smart grid utility node hanging on a pole in the middle of nowhere.
Exactly. At the physical edge, you have none of those data center protections. The hardware is exposed to the elements, and more importantly, it is exposed to malicious physical tampering.
And this creates a severe cryptographic problem, because if the physical environment is untrusted, software identity becomes deeply vulnerable.
Very vulnerable.
Walk us through the vulnerability. If I just buy a standard commercial router, configure it with a strong password, load my enterprise security certificates onto the hard drive, and bolt it to that utility pole, what is the attack vector?
The attack vector is a screwdriver.
Just a screwdriver.
An attacker doesn't need to launch a sophisticated cyber attack over the internet. They literally drive a truck up to the pole, pry the router off its mount, and steal the physical box.
Wow.
They take it back to a lab, pull the hard drive or desolder the flash memory, and extract your private cryptographic keys.
And once they possess those private keys,
They can load them onto their own machine, they can masquerade as your trusted edge router, establish a highly privileged VPN tunnel back into your core network, and completely bypass every software-based zero-trust check you have in place, because they possess the legitimate cryptographic identity of the stolen device.
so if we cannot protect the physical box with a locked door, how do we establish trust? How do we prove the device is legitimate without exposing the keys to theft?
We have to anchor the trust into the silicon itself. Software is malleable, silicon is permanent.
I love that phrase. Silicon is permanent.
Edge nodes operating in hostile environments must be engineered with a hardware root of trust. This is almost universally achieved using a TPM 2.0, a trusted platform module, or a dedicated secure element chip that is physically soldered directly onto the motherboard during manufacturing.
Let's dig into the architecture of a TPM, because it's not just a simple storage drive for passwords. It is an active cryptographic processor.
It is essentially a localized, highly secure, tamper-resistant vault and encryption engine combined.
Okay, so how does it get its keys?
During the hardware manufacturing process, the original equipment manufacturer, the OEM, generates a unique asymmetric cryptographic key pair. The private key is called the endorsement key, or EK. The OEM burns this private key deep into the silicon memory of the TPM.
And the critical distinction here is that the TPM is designed so that the private key can never, under any circumstances, be extracted or read by the main operating system.
Never. The operating system can send data to the TPM and ask the TPM to encrypt it or sign it using the private key, and the TPM will return the signed result. But the raw key material itself never leaves the secure boundary of the chip.
It is physically bound to that exact piece of silicon hardware.
Alongside this key, the manufacturer installs a manufacturer-installed certificate, or MIC, signed by their own root authority, which acts as a birth certificate for the hardware.
So when the energy company deploys that router out to the solar farm and powers it on, it initiates a zero-touch provisioning sequence, or ZTP.
Yes, ZTP. The router connects to the internet and reaches out to the central orchestrator. The orchestrator basically says, prove to me that you are the legitimate hardware I purchased and not a hacker laptop.
How does it prove it?
The orchestrator sends a cryptographic challenge. The router passes that challenge down to the TPM. The TPM signs the challenge with its burned-in private key and sends the result back.
And then the orchestrator verifies it.
The orchestrator verifies the signature against the manufacturer's public key. It cryptographically proves, with mathematical certainty, that this connection is originating from the exact tamper-proof hardware that was purchased.
Only then is the device trusted enough to download its operational configuration, its routing tables, and its enterprise certificates.
Exactly.
Okay, so the hardware is verified. We know the box is legitimate. But a modern edge gateway isn't just routing packets. It's running edge compute. It might be running a dozen different Docker containers or microservices locally. One container analyzing telemetry data, another managing local robotics.
Right.
How do we secure the communication between the software microservices running on the hardware? Because again, we have to assume continuous compromise.
If a threat actor finds a software vulnerability in one of those containers, we don't want them using that container's identity to move laterally.
Right. So what's the solution?
This is where we implement a framework called SPIFE, SPIFFE, which stands for the Secure Production Identity Framework for Everyone, and its runtime environment, SPI-ARO.
SPIFE and SPIRE are incredibly powerful tools for edge computing. What specific problem do they solve?
They solve the problem of long-lived static credentials. In a legacy environment, you might issue a security certificate to a database server that is valid for 2 years.
Right, which is an eternity in cyber time.
Exactly. If an attacker steals that certificate, they have 2 years to exploit it before it expires. At the physical edge, that is unacceptable risk. SPIRE manages ephemeral identity.
Ephemeral meaning highly transient, short-lived.
Extremely short-lived. Instead of issuing a 2-year certificate, the local SPIRE agent on the edge device mints highly specific transient certificates called SVIDs, SPIFE verifiable identity documents, for every individual microservice.
And how long are these valid for?
These SVIDs might be configured to be valid for only 7 days, 24 hours, or even just 15 minutes.
So the microservice uses this SVID to authenticate to other local services or to the cloud database. But because the lifespan is so short, if a threat actor compromises the container and manages to steal the certificate from memory, they have a microscopic window of opportunity.
Precisely. By the time the attacker exfiltrates the certificate and tries to weaponize it, the SVID has naturally expired. The cryptographic math simply invalidates it.
And the SPIRE agent just keeps rotating them.
The SPIRE agent continuously rotates and reissues these short-lived certificates in the background, completely invisibly to the application. It creates a constantly moving target that is practically impossible for an attacker to pin down.
But this reliance on constant certificate rotation creates a potential failure point. If these certificates are expiring every few hours, the edge device needs constant contact with the central certificate authority in the cloud to verify revocations and get new ones. What happens if the edge device is a cellular gateway on an oil rig and a storm knocks out the satellite backhaul? The device loses its internet connection. If the certificates expire, do all the local systems just crash?
That would be catastrophic, which is why edge architectures utilize local OCSP stapling.
OCSP.
OCSP stands for Online Certificate Status Protocol. Normally, when a service presents a certificate, the receiving service checks with the central authority over the internet to ensure the certificate hasn't been revoked. With local stapling, the edge gateway caches the revocation status and acts as a localized proxy authority.
It essentially downloads the latest master list of valid identities while it has an internet connection and holds on to it.
Yes. So if the satellite link goes down, the edge device can gracefully degrade. It relies on the localized cache to continue verifying the SVIDs of the local microservices.
Which means it can keep working.
This allows the edge gateway to maintain local control loops, keeping the oil rig drill sensors communicating with the safety shutdown valves, while ensuring that strict, localized, zero-trust security policies are still enforced, even completely disconnected from the cloud.
That is profound resilience. You maintain cryptographic security without sacrificing operational availability.
It's vital for industrial edge environments.
But let's bring it back to the ultimate physical threat. The guy with the screwdriver and the ladder. The hardware root of trust proves the device is real. The ephemeral identity protects the software. But what if the attacker isn't trying to spoof the device? What if they are physically trying to extract the TPM chip itself or tap the memory buses on the motherboard with a logic analyzer before the certificates expire?
That is where we deploy automated tamper response and zeroization. Because if an attacker has physical possession of the device in unlimited time, they will eventually bypass the hardware security. You have to assume the hardware will be compromised.
So how do you fight that?
Therefore, you must engineer the system to fail securely. Enterprise edge hardware is equipped with an array of physical intrusion detection circuits.
We are talking about physical sensors wired directly into the chassis enclosure.
Yes. Microswitches that trigger if the outer metal casing is opened, optical sensors that detect ambient light if the lid is removed, accelerometers that detect if the device is being violently ripped off its mounting bracket.
If any of these environmental sensors are tripped, it indicates a severe physical breach.
And the immediate response is devastating. The sensor triggers a high-priority, non-maskable hardware interrupt directly at the CPU level.
Meaning the CPU has to drop everything and listen.
Exactly. The operating system immediately halts all standard processing and executes a cryptographic zeroization protocol. This happens in milliseconds.
What's the first step?
First, the system instantly cuts power to the volatile memory, the RAM, destroying any active data, session tokens, or unencrypted data structures that an attacker might try to read with a cold boot attack.
It kills the active memory.
Simultaneously, a command is sent to the TPM chip instructing it to enter a permanent lockout state, rendering the private endorsement keys completely inaccessible even to the host operating system. The cryptographic vault is permanently sealed.
Okay, RAM is dead, vault is locked. What else?
Next, internal flash erasure routines are triggered, which actively overwrite and purge all cache telemetry, localized databases, and routing configurations stored on the solid-state drives.
So the device is actively wiping its own hard drives while the attacker is unscrewing the lid.
And finally, as a dying gasp, the device attempts to send an emergency telemetry packet out its network interface to the upstream orchestrator, essentially shouting, "I've been physically breached, revoke all my certificates, isolate my switch port, and assume I am compromised."
A literal SOS message.
And then the device powers down, permanently bricked.
So by the time the attacker gets the lid off and connects their logic analyzer to the motherboard, they are probing a dead piece of silicon. The data is gone, the keys are locked, the network port is isolated. The router essentially self-destructs its own brain to protect the broader network.
It is the absolute ultimate expression of zero trust. It is the only way to guarantee the integrity of the network when the physical perimeter is completely absent. You engineer the edge to be entirely expendable.
This has been an incredibly deep dive into the mechanics of modern networking. We have covered a massive amount of technical ground today.
We really have.
We started with the failure of MPLS routing and the trombone effect. We moved through contextual risk scores, SASE architectures, and single packet authorization. We explored the intricacies of VRFs and tag-based microsegmentation in the data center. And we just unpacked hardware roots of trust and cryptographic zeroization at the edge.
It's a lot to take in.
It is. But as we move to the outro, we need to synthesize all of this. For the business leader listening, the C-suite executive who have to authorize the budget for this massive architectural overhaul. What is the overarching value proposition?
The primary takeaway for leadership is a shift in perspective. Historically, network security was viewed as a necessary friction. It was a cost center that slowed down the business.
Always getting in the way.
The legacy castle and moat model actively hindered agility. It made adopting cloud services painful and slow because of backhauling. It made remote work a frustrating, latency-filled experience for employees. It forced the enterprise to sign multi-year contracts for rigid, expensive MPLS circuits.
And the tragic irony is that despite all that expense, all that friction, it left the company massively vulnerable to lateral ransomware attacks.
Precisely. It was expensive, slow, and ultimately ineffective.
So how does zero trust change the business value?
Zero Trust Network Access is not just a security upgrade, it is a fundamental business enabler. By moving the security enforcement away from physical perimeters, by decoupling it from IP addresses and attaching it directly to user identities and workload metadata, you unchain the organization.
You are finally free to securely embrace multi-cloud environments, deploy a global hybrid workforce, and scale out vast Internet of Things architectures at the edge.
Exactly. You allow the business to move at the speed of the internet without the paralyzing fear that a single compromised laptop at a coffee shop is going to result in a network-wide ransomware collapse.
You align the security architecture with the agility required by the modern business. It takes the brakes off the car.
It creates a resilient, elastic enterprise. But as we look forward, the trajectory of this technology points toward an even more radical future. We promise to leave you with a final provocative thought to mull over, something that builds on everything we've discussed today.
We started this deep dive by observing the collapse of the physical walls. Then we watched the security controls detach from the network layer and move closer to the applications themselves. But think about the logical conclusion of this trajectory. We are witnessing the complete virtualization of trust itself. What happens when the very concept of the internal corporate network ceases to exist entirely?
It is a fascinating thought experiment that is rapidly becoming architectural reality. Imagine a future where the corporate LAN is completely obsolete. There is no corporate Wi-Fi network in the office buildings, no internal subnets, no enterprise WAN connecting branch offices.
None of it.
Instead, every single application, every database container, every employee laptop, and every edge sensor simply connects directly to the raw public internet.
But they operate as sovereign cryptographic islands. A world where every asset relies entirely on hyper-localized microsegmentation, identity attestation, and MPLS tunnels to communicate. The network becomes nothing more than a dumb transport layer for encrypted traffic.
The concept of inside or outside the network vanishes entirely because the perimeter has dissolved down to the atomic level of the individual microchip.
We are watching the complete dissolution of the perimeter. The network is everywhere, and the network is nowhere. So keep questioning your own architectural assumptions. Keep interrogating your own network perimeters, because the walls you think are protecting your data might just be an illusion, and the moat you built might be the very thing holding your business back.
Very well said.
That is all for this deep dive. Thanks for joining us as we decode the technical networks that connect our world. Keep questioning, keep verifying, and we will catch you on the next deep dive.